Hello everyone. Welcome to AAA634 course. The name of this course is Advanced Processor Architecture. And then I said the main topic of this course is exploring accelerator architecture. So recently the accelerator is the very important research topic in academia and industry, especially on computer architecture research area. So that's why I set the topic of the discourse as the accelerate architecture. So this time I will introduce about the discourse, and then I will introduce the domain specific architecture. So let's talk about the object of this course. So actually, I decide to provide this course as the real-time online course because of the COVID-19 pandemic. But this time it's the first class of the discourse. But recently the HPCA is the top tier computer architecture conference. And then HPCA is holding in Seoul, actually virtually. And then I'm serving as the arrangement chair. So because of that, I think I cannot teach this course in the morning because even though the conference is held in Seoul, the conference time is set uh, as the EST, that is the East Coast Standard Time. Actually, it's the New York time. So because of this time gap, I need to awake during the conference period. So I think I don't believe I can teach this course in the morning, right? In the Korean standard time. So that's why I record the first class of this course, and then and so this is some special case. So sorry about this recorded course, but yeah. So let's talk about the object of the course. So the object of this course is to explore modern process architecture, especially focusing on domain-specific architecture. And then this domain-specific architecture is called DSA in acronym. Also, this domain-specific architecture is called the accelerator architecture. So recently, the accelerator is the very hot topic in computer architecture research field. Why? Because of machine learning and artificial intelligence. So actually, and then this machine learning is implemented on the neural networks, and then the neural networks actually is the series of linear algebra calculation. So that means the matrix of calculation. So the matrix is the set of the large number of data. And then in order to calculate this large matrix, we need the very high performance processor, computer processor. But so as you know, so for the matrix computation, we need the lots of iteration loop, such as the nested for loop computation, as you know. So, and then this computation is not suitable for the, what's that? It's a single thread application. That means single thread application means that the every instruction is executed sequentially, but this matrix of computation is not suitable for the sequential computation. So actually the parallel computation is required for this matrix computation, matrix calculation. So but recently the specific processor, it's also the computer processor. So that runs on the computer system. So it's a large computer system such as a server or cloud infrastructure. So this is the computer processor, but this computer processor is designed for specific domain, specific application domain, such as neural networks or artificial intelligence. Some other applications such as graphics or AR, so augmented reality or virtual reality. So graphics applications. So this type of processor is called accelerator or domain-specific architecture processor, like a DSA. So in this course, we're focusing on the accelerator architecture, and especially I will teach about the stroke architecture of the deep neural network accelerator. Okay, so so actually this is the first course that actually this is the first time I teach this course, this topic for the first time. Actually, this is the very cutting edge course. So cutting edge topic, so very new topic, and then it's not frequently provided in the academia course because this accelerator is the very recent topic in the computer architecture field. So I believe you are very familiar with the computer architecture course because the computer architecture is the mandatory course in the computer engineering and the computer science department. But we just in the computer architecture course, we learned about the very old type. Such it's also very important topic, but some old generation of the computer process architecture. And then actually the last year I taught about the advanced computer architecture course. It's AAA634. So in that course, I taught about the out of order processor architecture. That's also very important because the most of the modern processor has the out of order processor architecture in order to exploit the instruction level parallelism. Then why instruction level parallelism is required in order to increase the performance. So that's also very important topic, but it's also it's a traditional topic actually. So recently, many researchers and many academic researchers and or industry researchers are focusing on some specific process architecture called the domain-specific architecture. Is it because the technology is changing? So I'll talk about this technology trend later. It's actually today. So that's very important, but it's very new topic. 네. 그러니까 이 과목에서는 저는 이제 그 domain specific architecture에 대해서 이제 소개를 할 거고요. 특별하게 이제 DNN, 그 Deep Neural Network Architecture에 대해서 좀 다뤄보는 시간을 가지려고 합니다. 근데 이제 이게 그렇게 이제 딱 정립이 된 그런 뭐라 그럴까 학문적인 그런 것이 아니라 굉장히 이제 recent topic, 그러니까는 cutting edge technology라고 할 수 있겠죠. 그러니까는 뭐라 그럴까 그런 트래디셔널한 그런 학문적 영역보다는 지금 굉장히 뜨고 있는 그런 학문적 영역이라고 이제 볼 수 있겠고요. 그렇기 때문에 조금 아직까지는 이렇게 딱 정형화된 그런 이렇게 뭐랄까 그렇게 진행이 되지도 않을 수 있는데 어쨌든 이 코र्스도 제가 이제 처음으로 이제 가르치는 거기 때문에 처음으로 이제 디자인을 하고 가르치는 거기 때문에 아직 그렇게 딱 이제 픽스가 돼서 좀 안정적으로 이렇게 뭔가 메토리얼이라든지 이런 부분들이 이제 준비가 되진 않았습니다. 그런 거는 이제 좀 염두를 하고 들으면 좋을 것 같고요. 어쨌든 그래도 이제 저도 이제 공부를 하면서 이렇게 이제 최신의 페이퍼 읽고 이렇게 하면서 공부를 하면서 이제 좀 가르치려고 하고 있고, 뭐 약간 이렇게 뭐랄까 딱 약간 이제 뭐랄까 혼란스럽다 볼 수도 있는데, 그래도 이제 잘 따라오면서 서로 공부하면서 연구하면서 잘 들었으면 좋을 것 같습니다. Okay, so I'll briefly I'll briefly tell what will be covered in this course. So especially I will focus on the DNN, is a deep neural network accelerate architecture and design issues in this course. So what is the DNN? So actually this deep neural network is widely used for training and inference of the machine learning applications. Actually, this DNN structures, so deep neural networks is widely used for image processing or video processing applications. And then so with this DNN, so we handles some very dense data, like such as the image and video data. So that means the computer processor requires the very heavy computation capability for this DNN computation, the DNN operation. So that's why we need the accelerator. So accelerator is, what is the accelerator? So accelerator is some specific processor designed for running some specific domain applications. So what is the most popular accelerator? Recently, the graphics processing unit, GPU. So GPU is designed for graphics applications and then image processing and video processing applications. And then, so that means the GPUs are specified for computing some image data, like pixel data. And then, as you know, in the digital image, the pixel data composed of very the one image frame, and the one image frame is composed of a large number of pixels. That is all data, some data. So in order to apply some image processing algorithm, so we need to apply so it's a kind of a matrix application. So for this parallel processing and image processing algorithm, we require the GPU, graphics processing unit. So that is the kind of accelerator or domain-specific processor or domain-specific architecture. And then in this course, also we will explore about the research issues and research topics in deep neural network accelerator. Okay, that is the main theme of this course. And then we will cover the overview of DNN. So the first we need to, in order to design some specific processor or ASIC, it's very similar to ASIC or some chip. So in order to design some specific processor, we need to understand some algorithm of some domain or algorithm of application. So the firstly, we will slightly, I'm not a specialist of the what's that? It's a machine learning application or machine learning algorithm or neural networks. So I'm not specialist. So if you are interested in the specific neural network algorithm or some specific some other specific neural networks, then please take some other courses like the deep neural network or machine learning. so I slightly covers some teach about some overview of deep neural network and then design spaces. And then it's very important. You not design the accelerator. We need to specify the main computation kernel of the some application domain. So as I said, the deep neural network equals the heavy computation of matrix operation, as a matrix computation. So that means that is the some specific kernel. So what's the kernel? Kernel is the some main computation function that should be performed in the computer processors. So we need to specify the representative deep neural network kernel. So we will explore what is the characteristics of the deep neural network kernel. Okay, then we will discuss about the DNN accelerator design issues. So what is the design issues? So when we design some processors, what is the goal of this design? Like a research or some architecture design, high performance and low cost. It's also applied to accelerator design or accelerator architecture. So we will talk about the DNN accelerator design issues. So we need to optimize the accelerator design, and then I will discuss about the processor in memory. So this the matrix operation, so matrix multiplication or some some other matrix operation is can fit to the some structure of the memory, because the memory is composed of what's that? It's the pin line and the word line. So if we see that this memory structure is very similar to the matrix structure. So actually, this memory is used for storing digital data, but using some characteristics, using the analog characteristics of these memory cells or memory structures, we can apply some matrix operation in the memory. So actually, in the new type of the memory, not DRAM or not SRAM, it's a new type of memory. So I will slightly discuss about this processor in memory or near data processing for neural networks. So that is some tentative plan of this course. Okay. So this is the textbook of this course. So I will mainly use the efficient processing of deep neural networks, and written by Vivian Zhe, Yuxin Chen, and Tianzhi Yang, and Joel Immer. So Vivian Zhe is the MIT professor, and then she is very famous for designing neural networks, hardware neural network. So she's very famous professor. So she originally works for the process architecture for image processing, but this image processing is related to the neural networks, because the recently neural networks are widely used for image processing and computer vision. So she's worked for this neural network hardware design research. So she's a very famous researcher in this field. So I will use this book as the main textbook of this course. And then I will provide the lecture slides every class. And then also I will introduce some research papers to read in this course. So So I will use these materials as some course materials in this course. Okay. And then course material lecture slides will be provided, and then I I plan to use some architecture simulator for this accelerator architecture course, but it's not fixed yet. So actually, Iris, this is the very famous neural network architecture simulator, and then it's developed by Vivian Ze. Okay, Vivian Ze. So I may use this architecture simulator or some other architecture simulator such as Gen 5 Aladdin, but Gen 5 Aladdin may be somewhat complex, so it's not fixed yet. So it's so just a plan. And then prerequisite is a very so you need to know about the basic concept of the computer architecture, and then which is covered by COSE 222. So this is the computer architecture course for the undergraduate student. So I assume that you already know about some main concept of this computer architecture, undergraduate computer architecture course. It's like pipelining, and then memory hierarchy, and some memory subsystems. So it's very, so you need to understand the very basic concept of computer architecture. Also, the last year I taught the advanced computer architecture course. So it's AAA 514. So in this course, I taught about the out-of-order processor architecture, and then some related research topics in the CPU actually. So CPU. So but I believe most of the students enrolled in this course is a new graduate student. So I believe they do not deeply know about this out-of-order processor architecture. So so in the first 2 or 3 classes of this course, I will review this out-of-order processor architecture before diving into the accelerator architecture. So do not worry about this, but I hope you are you are familiar with some important concepts of these computer architecture topics, such as the out-of-order processor or some other topics. So if you are interested, then you can find my YouTube channel with the Gonjaku, Gunjakoo, and you can find the recorded videos in my YouTube channel. Subscribe. 뭐였죠? 좋아요와 구독이었나? So you can find the recorded video in my YouTube channel. I'm not advertising. So if you are interested, you can watch this recorded videos for advanced computer architectures. Okay, and then some basic knowledge on programming languages such as C or C++, because the most of architecture simulator is written in C or C++. So, and then as a computer engineering or computer science student, I think I recommend you to understand the C programming or some. I believe you can write some basic C applications. And then basic knowledge on Linux operating system, because the most of architecture simulator will work on Linux operating system, not Windows. So So getting familiar with this Linux operating system. So do not use the Windows. So we need to use the Windows because of the Office programs or some other applications, but please get familiar with the Linux operating system for your research and then your work. Okay. So instructor, my name is Konje Ku. It's a Kugonje. And then my office is 우정정보관 43, and then it's office hour. So it's a Monday, 1:30 p.m. to 3:30 p.m. And then this is my email address. So if you have any questions or issues, then you can email me with this email address. And then also, I will introduce about some class management tool later. The research area. So generally my research area is computer architecture, and also I'm focusing on the GPU architecture, one memory storage system, and the embedded system, and the accelerator, like this class, or FPGA. So this is my main research areas. Okay, for the course management tool, I will use the Korea University Blackboard. So it's this Blackboard. So actually, every class is managed by this Korea University Blackboard. But so in the Blackboard, I will post the announcement for this course, and then I will post the assignments or projects. So I will upload the lecture slide and lecture videos on the Blackboard. Okay, but Blackboard is not a convenient tool, so that's why I used another tool for the class management. But for this course, I will use I use the Piazza for the class management tool, because with the Piazza, students can post their questions conveniently, and then actually the many students can discuss about some topics, and then also they can answer for the other students' questions. But most of the question was answered by me or TAs, actually. But but for this course, actually the number of students enrolled in this course is not large. It's about, I believe it's about 10 or slightly more than 10. So I will use Teams for this course. So this Teams application is very similar to the Slack. So what is the Slack? So Slack is how can I define the Slack? So in the Slack is some communication tool for the workspace. Actually, we can use the email, but as you know, the email, so many people sent me many various type of the emails. So it's not easy to it's not easy to manage this tons of emails in my email account. So, but I don't like KakaoTalk, because so the KakaoTalk is also has some very, so it's also a private messenger. So we use the KakaoTalk for some individual purpose. So for the works, so for the purpose of some work or research, many people use the Slack. But we can use the Teams. So actually, Teams is developed by Microsoft, and then if you are the so I believe everyone is the Korean University students. So if you registered in this Korean University or graduate course, then you can use Teams or Office programs freely. So this Teams is very similar to Slack. And then I will generate the workspace for AAA634, and then I will invite student to this workspace. And then I will generate some channels for discussion or some assignments or project. And then you can, I hope many students discuss proactively using these teams, okay? So I will invite later for the, I will send the invitation link for this AA634 Teams workspace, okay? So this is my actually first attempt. So I'm not familiar with the Teams, but I'm using Slack for the HPC arrangement, but it's very good actually. So I will try to use Teams for this class management, okay? And then grading policy, it's a tentative, it's not fixed yet. So I plan to take, we will plan to take a midterm exam, and then maybe there can be a project or some assignments. So, but do not worry about the some grade for this course, okay, actually. So exam is it will be closed book exam, and then no electric devices are allowed. And then it's cheating, it can be F for this course, and then you can answer in Korean or English. So actually this is the English course, so I try to teach in English. But if you have any questions, or if you do not understand about some topics, you can ask question in Korean, then I will answer in Korean, okay? So do not worry about the language. You can, so, I mean, you can use Korean, okay? So teach in English is my duty, so it's not your duty. So you can freely use Korean during the class, okay? Yeah, this is the tentative schedule of this course. And then this is the first class, the first day of the semester, and then this is the first class. Okay, so I will introduce about this course in the first class, and then I will read about some. I will leave some computer concept of the computer architecture or some topics like processors or memory systems in the upcoming 2 weeks. 2 weeks, okay? 2 classes actually, and then I will briefly introduce about some domain-specific architectures or domain-specific processors, and then as I explained, so what will be covered in this course is an overview of deep neural networks, the design objective, some accelerator design issues, and then operation mapping, and optimization. So, and then the midterm is planned on May 19th, but it can be changed. So this is the planned, okay? And then processing in memory, then it's a final project presentation or final exam. So this is the end of the syllabus. If you have a question, then you can email me, or I will make this workspace for this AAA 634, and then I will also invite some students, the enrolled students enrolled in this course to this workspace. So then you can use these Teams. Okay. Okay, and then Okay, let's talk about the domain-specific architecture. So this is the first class. I will introduce about the domain-specific architecture and then why accelerator is required for modern processor or modern computer systems. So goal of this first class is to understand why accelerators are required for today's computer systems, not yesterday's computer system. It's a previous. So old generation of the computer system. And so actually, when we talk about the computer system, that means it's the kind of CPU architecture or GPU architecture. So you know the GPU is firstly developed in 1980s. So it's very old. But recently, GPUs are widely used for some parallel applications and the scientific applications and also machine learning applications. So GPU is the kind of domain-specific architecture, but in the today's course, I will explain why accelerators are required for modern computer system, today's computer system. So what have we learned? We'll discuss about the Moore's law and technology trend. So because of this technology trend, the computer architecture fields are also changing dramatically, actually. And then, so that's why we need the domain-specific architecture or accelerators. So, and then I will introduce about to the domain-specific architectures. Okay, let's see this slide. So what can you see? These are computers. And then actually very old generation of computers, computer systems. So and then, so why do I show these old computers? So what is this computer? It's I think this is the first personal computer developed by IBM. So actually the personal computer was developed by IBM, and then but the IBM does not work for personal computer system actually. The IBM is actually the what's that? It's a kind of a software company where also IBM built the server computer systems. So it's a it's not customer. The IBM is not a customer company. Okay, 뭐라고 하죠? 기업 상대로. Okay, anyway. So this is the first personal computer developed by IBM. And then what is this? This is the Apple computer, Apple III actually. It's a very old. And what is this? It's a Macintosh. It's a very fancy and beautiful computer, also developed by Apple. So what is the computer architecture? So I believe the student taking this course is interested in computer architecture. So what is the computer architecture? It's the study on computer systems, focusing actual computer hardware, where computer hardware and software interfaces, also the computer system infrastructure such as cloud systems or server systems, or some area of system softwares like operating systems or drivers and hardware drivers. Okay, but computer system is so complex. So that is this slide shows the picture of main board, and then I believe if you are a computer engineering student, I believe you can assemble the computer system, personal computer system actually. So I believe you you have seen the computer main board. so, so actually, this is the very old generation of a computer main board. So as you can see that this North Bridge, but recently this North Bridge chip is included in the CPU. So the modern mainboard does not have North Bridge chip, but this is the old mainboard photo. So you can find this North Bridge chip. So why do I show this photo of mainboard? I want to say computer system is very complex. So, and then the computer system is composed of many components. That's true, right? So this is the socket for CPU, the central processing unit. And as you can see, this is a North Bridge, but as I said, the modern CPU includes this North Bridge chip. So actually, through this North Bridge chip, the CPU is connected to the DRAM. So this is actually it's an AGP slot, but the modern main board has the PCI slot. So, and then the modern computer system, like the PCI, like a VGA slot, is directly managed by CPU also. Okay. And then as you can see, you can find that this South Bridge chip, and that this is the mainboard chip. And you can find the many slots, and then you can find the I/O ports here. So these are all components of the computer system. And then using these various components, we build a computer system. So these are some area of the computer architecture. So when we say about this computer system includes these various type of components, okay? Like a CPU, memory, and the input output devices, networks, also the mainboard chip, PCIe. So these are all included in the computer system. So, and then if you work on the computer system research, that is the computer architecture research. But in the narrow meaning of the architecture research means the research on computer processor. It's a narrow meaning, okay? So what did you learn in the computer architecture field? I believe most of the students took the computer architecture course for undergraduate students, and then in Korean University, this course is the COSE 212, 222. So in this course, you learned about the pipelining, memory hierarchy, and or memory systems, and instruction set architecture. So these are very important topics in computer architecture. So it's a very, very basic of the computer architecture, actually. So that means you need to understand about the pipelining, memory hierarchy, or instructions and architecture before taking this course, right? So this is a very basic, actually. And then also when we mention about the research on computer architecture, so I said it means, in the narrow meaning, it means the research on processor. And then so it's traditionally CPU. And then for the modern CPU has the out of the order processor architecture, like Intel CPUs, or also the AP, like application processor in smartphone. These processors has the out of order architecture, is an OOO architecture. So actually, I taught this out of order process architecture last year, spring semester of last year. So hopefully I want students taking this course also can understand about this modern CPU architecture, but it's not mandatory. So, but I want the students can understand about some the basic concept of this CPU operation. Okay, so why? So so you need to answer why the CPU is designed for single thread application, and then why the CPU architecture, why CPU process architecture is suitable for this single program or single thread application. And then so there are some various topics for this out of order process architecture also, like a branch prediction, or very complex topics. Okay. But so traditionally, when we talk about the computer architecture, then that means it's called the process architecture. And traditionally, it means the architecture of CPU. Like this. So this photo shows the Intel Xeon chip, and then the die photo of the Intel. Actually, this is the die photo of the Intel i7. So like a CPU. So we focus on some architecture of the CPU. Why? Because the CPU is the very critical and important component in the computer systems. Why? The instructions are executed in CPU cores. Okay, that's why CPUs are very important. So we learned about some basic concepts of the process architecture in the previous courses. But the CPU architecture is also very complex. So as you can see, this dipole, I believe. So as you know, the Intel Xeon processor includes the billions of transistors, and then that means the process architecture is also, the CPU architecture is also very complex. So we can understand the architecture of this processor with this dipole. So this slide shows some block diagram of the Intel I think it's the i7. So Intel i7 processor is a core processor. So as you can see, the processor is composed of front end. The instructions are fetched and the instructions are decoded in the front end. And then instructions are also executed in the execution engines. So this is some basic out of order process architecture of Intel processors. And then as you know, these processors has the memory system, so level on cache is a private cache. So this diagram shows the basic structure or basic architecture of the Intel out of order processor architecture. Okay, so this is, but as you can see, this is also complex. Okay. So why CPU is important traditionally? Because so why do we learn about computer architecture or computer system? So computer architecture for better for yielding better computer systems. So what does better mean in the computer systems? Fast. Fast means high performance. And then second, low cost. What is the cost? It's the some cheap area and what is the power or energy. So energy is also included this performance. So low cost and then high performance. So that is the actually the goal of our computer architecture research, and then also it's the goal of the computer system research. So why CPU is important? The performance of a computer system traditionally, so focus on the word traditionally. So traditionally, the performance of a computer system is proportional to the performance of CPU. So that's why the CPU is very critical and important component in the computer system. And then the process architecture of the CPU is so critical for the traditional computer system. And then this performance of a CPU is limited by memory bandwidth or latency. And this is called the memory wall because the speed of the memory system is slower than the speed of a CPU. Also, the performance of this entire computer system is limited by slow storage devices, and then limited by slow input and output device performance or network performance. So, right? These are very slow. So, for the traditional computer system, the CPU is very critical, and then CPU performance determines the performance of entire computer systems. So that's why what you need to remember is the traditional computer system. Okay, then let's talk about some technology trend and then Moore's law. So what is Moore's law? So Moore's law, I believe the Moore's law is the most famous law in computer architecture field. But I know the Moore's law is a very simple law, and then it's not a theoretical or it's not theoretical law, it's just empirical law. So it is related to the economics, not research. So what is the Moore's law? The number of transistors will double every 2 years. So this is the Moore's law. So number of transistors in a single CPU chip or in a single processor chip will double every 2 years. This is the Moore's law. And then this Moore's law is firstly developed or found by Gordon Moore, is one of Intel founders. So I said this is the empirical law or economical law. So that means the processor designer or process architect set the goal of their new processor the goal of the new processor to track this trend of Moore's law. So what does that mean? So this is the older processor, older CPU, and then so Intel engineers trying to make the new CPU. So and then when they design the new generation CPU, then they try to track this Moore's law. Like the number of transistors in the CPU can be double in 2 years. So when we compare the number of transistors in the CPU chip, and then this is a new CPU, that's a CPU of the 2 years ago, then the number of transistors can double for this new CPU. That is the Moore's law. Then why? So actually, the so CPU developers or CPU architect set the goal of this new CPU using this Moore's law. Then why Moore's law is important? Because this is some technical trend. So actually the Moore's law set the goal of the technology advance, and then also this Moore's law set the goal of the development of CPU or processor. So this is the definition of the Moore's law introduced in Wikipedia. So I copied this Wikipedia contents here. So as you can see, so doubling. So it was, so originally it was doubling every year, but in 1975, the Moore's law is, so he revised the forecast to doubling every 2 years. So it was also changed, modified. Okay. But why is Moore's law so important in computer architecture field? So let's think about the customer side. So if we are a customer, then so if we want to purchase the new computer system, so you expect that the performance of the new computer system should be better than the performance of an old computer system, right? So, and then based on the Moore's law, the technology is also developed, so improved, and then so using the forecast by this Moore's law, the CPU architect or some CPU engineers set the performance goal of the new CPU product. Okay, and then using if the performance of a new CPU product is better than the some old performance of the older generation CPU, then customers will purchase this new computer system. So that's why the Moore's law is important. So I said this is some kind of economical law, but this law forecasts the development of the advance of the computer system very well, and very well until the 2000 until 2010 or some recently 2015. So this graph shows the number of transistors on the integrated circuit chip from 1971 to 2016. So as you can see this, so you can see this is this y-axis is the log scale, and so and then this is the time, each year. Then you can see the trend of the number of transistor. Transistor is a nearly what's that? It's a linear, nearly linear. But as you can see, this y-axis is the log scale. So that means this trend is very similar to the forecast by Moore's law. So that means the number of transistors double every 2 years. But this trend is slowing down recently. That's the very critical technology change in the computer system field or computer architecture field. Okay. So let's see the microprocessor trend. So as you can see, this x-axis is the year, that's the time, and then y-axis is the some kind of a number of transistors and single thread performance, and frequency, power, number of logical cores. But as you can see, this is also log scale. Okay. So let's see the number of transistors here. This is so linear. So that means until 2000, late 2010, the Moore's law is kept. So based on the Moore's law, the technology advanced. This graph shows until the 2000, maybe 15 or 16, but recently the Moore's law is slowing down. So that means it's very hard to make better processors. It's very hard. So let's see the performance of the single thread performance. As you can see, the performance is saturated. What does that mean? For the single thread application, the performance is saturated. And then that's true. For the personal computer system, the performance of this Intel single core is nearly same to the old generation CPU, right? And then frequency is also saturated. So, and then power is increased and then also saturated. But as you can see, number of logical core increases. So what does that mean? So recently, so let's see here. Actually, the performance of single core is saturated early 2000. Before 2010. Then how can we improve the performance of a CPU? With multi-core. That is the technology trend, but this trend is also slowing down. So that's why the computer architecture requires some different type of processor, not CPU, and some specific kind of processors. Okay. So, but the Moore's law is not always subtracted by the commodity CPUs. So as you can see, in the first the performance of the single core CPU is increased by 25% per year. And then after 1986, the performance is increased by over 50% per year. So it's very huge. How it's the architectural advance. So the lots of architectural ideas are applied to the CPU architecture. So that's why at the 1980s, the late after the late 1980, the performance of the single core CPU is increased dramatically. But as you can see, recently the performance is increased by 22% per year. So actually, it's great also, but it is saturating. So what is the fundamental changes? What are the fundamental changes in modern technology? It's very important because the technology is changing. That means so the computer processor can be designed and manufactured based on the semiconductor technology. And if technology changes, so this trend will also change. So that's why the technology trend is so important, critical for the computer architecture research. Okay. In the technology side, the Dennard scaling ends already. So what is the Dennard scaling? The density of the power consumption is maintained in the same area, in the unit area of the CPU. That is the Dennard scaling. So how can this Dennard scaling is maintained? So this transistor size shrink because the channel length of the CMOS transistor also reduced, the size of the transistor shrinks. So if the channel length is reduced by n times, that means the size becomes the 1 over n. Actually, the size of the transistor is the 2D, is a two-dimensional. So that means the size of the transistor is reduced by n over 1 over n square. Okay, but as this channel length shrinks, we can increase the system frequency of the system clock. So that will increase the power consumption. But also the power consumption can be also reduced because we can use the lower supply voltage when the channel length reduced. So combining these all factors, then the power density of the unit area is the same, it's maintained, when the channel length of the transistor is reduced. That is the Dennard scaling, but it also ends. So what is the benefit of the Dennard scaling? So if we can reduce this channel length of the CMOS transistor, then we can build a faster CPU. This is a high performance CPU, but this CPU does not consume more power. So there's a similar power. That is the benefit of the Dennard scaling. But it ends. So that means even though the channel length of the CMOS transistor shrinks, but the power consumption is not reduced by does not decrease by this scale of the transistor because of some other factors such as the leakage current and then some other factors. So the power will be more consumed in the modern processor, and that's very critical actually. Okay. Then ending of Moore's law is transistor improvement slows. It's also critical. That is the technology trend. So recently Intel struggles to manufacture the new so what's that? The narrow channel length, the transistors that has narrow channel length, like so. So recently, the Intel is struggling very much for manufacturing small transistors. So that means the Moore's law is ending. So that means transistor improvement slows down the architectural. So for the architectural side, so limitation and inefficiencies in exploiting ILP. What does that mean? The performance of a single processor is saturated. So actually the performance of the single processor is increased by exploiting instruction level parallelism. So what does that mean? In the processor, many instructions can be concurrently executed in the concurrent by single core CPU. But even though this technology advance stops in the early 2000, so uniprocessor era ends in 2004, and then when the unicore era ends, then we improve the performance of the CPU with the multi-core, like MIMD architecture. But with this multi-core architecture, we can increase the performance of parallel, the thread level parallelism. That is the thread level parallelism. So we can increase the performance of parallel processing, not single thread performance. So, but this performance improvement is limited by the fraction of that can be parallelized. So that is the Amdahl's law. So if the application has the very limited fraction of this fraction that can be parallelized, then the performance is also saturated. So when the Amdahl's law is applied, the multi-core era is also ending. Also, the Intel or AMD includes the new instructions for multimedia and then the parallel computation such as the SSE or AVX. But this advances also is limited by the portion of the apply of instructions. Okay. So it's a very actually very sad news for it can be very sad news for computer architect, but it's not sad actually. And then product, let's see the product of the computer system. And then traditionally the computer means that it's the personal computer or supercomputer systems. But recently this computer product is moving to the IoT and the mobile or cloud infrastructure. So mobile devices. So and then I believe, so you change your smartphone or tablet every 2 years, but you do not change your laptop or computer, personal computer in every 2 years. Right? So that means the computer product moves to the mobile devices. Also, as mobile device is pervasive, so we use the large cloud infrastructure, so large server computer systems. So cloud also. So the Google data center or Naver or Paco data center, the Microsoft data center is very large, and then it includes the large number of supercomputers. So it's larger than the soccer stadium. So that means the mainstream of the computer system is moving to the cloud. Okay. So this graph just categorized how the performance of the computer performance of the single core processor increased by which by years, and then what is the reason of the advanced of single core performance. So before 1985, so I copied this. I copied this figure from the Patterson and Hennessy's Turing lecture. Why it doesn't work? I don't know why. Okay, let's see. So first, so the first letter is a Z-scalar, and the performance is improved by 22%, and then the RISC-scalar. So actually, the Patterson and Hennessy invented or developed the RISC architecture. So with the RISC architecture, the performance of the computer processor increased by 2x per 1.5 years, the 5% per year. So end of Dennard scaling as the power density increases per unit area. So we apply the multi-core architecture. So with this multi-core architecture, the performance is also increased, but this performance is increased for the some parallel part. And then slightly we used some new instructions for multimedia and some other instructions, and so it's the Amdahl's law. So it's slightly increased, but after 2015, it's just saturated. So like, so doubling may take over 20 years, like 3% per year is the performance of the single core processor. It's very tragic. Let's see the Moore's law in the DRAM technology. So before 1997, the density of the DRAM increased 2x, like the increase 1.5 times per year. So it's a bigger than 2x per 2 years. So it's higher than the Moore's law. So yeah. And then after that, until the 2010, the density of the DRAM is about the density of the DRAM doubles in 2 years. So it's just very similar to the Moore's law. And after that, it's the 1.1 times per year. It's the 2x, it's a doubling in 7 years. So what does that mean? So Moore's law is also saturating in DRAM, that means the memory technology. And for the processor, the Moore's law is slowing down. So as you can see, this is the trend of the Moore's law, but the real trend of the Intel processor is lower than the trend of the Moore's law. All right. Okay. Again, and then Dennard scaling. So I said that Dennard scaling means that the power density is maintained and the CMOS technology advances, but as you can see, the relative power per unit area increases dramatically. So that means Dennard scaling ends. So technology is also advanced. That means we can apply the narrower channel length for the CMOS transistors, but as the NR scaling ends, the power density for CPU or processor increases. It's also very critical. That means our CPU chip will consume more power. So that's why the power management or some other technique or DVFS technique is very critical in modern CPU. So what is the so what is the problem? So technology is saturated. So saturating. The Moore's law is ending. The NR scaling ends already. That means the computer processor will consume more power, but it's very hard to increase the performance of a processor. So it's very hard to build better processor using the modern technology. That's the critical problem. So why DSA? Why DSA, domain-specific architecture, is required for modern processors? So let's see why it doesn't work. Oh, it works. So let's see this slide. This slide shows some intuition, very good intuition to us. So this slide shows the energy per operation and instruction. So let's see the RISC instruction. It's a normal instruction. So this is the energy consumed by ALU, but what is the overhead? Overhead is much larger than the energy consumed by ALU. So what does that mean? What is this overhead? This overhead is a kind of a pipeline control, instruction decoding, instruction fetching, and then rollback, so, and then prediction and speculation. So these overhead are included in executing one instruction. And if the instruction is the load store instruction, then this load store instruction need access memory. So this energy for accessing memory is included. So it's over 150 picojoule. So it's a 125 picojoule. But as you can see, ALU consume much lower energy. So that means for executing some instruction, actually the execution engine does not consume much energy. So in order to execute the instruction, we need very small amount of energy, but lots of energy is consumed for overhead to execute the instructions. Right? What this overhead? This overhead means the instruction fetching, decoding, and then pipeline control, and some other overheads. It's very large. That's why the computer processor is very complex, and then that's why the computer processor consumes much energy, much power. But what is the benefit of a computer processor? Programmability. So let's see the single point floating point operation. It's about the 15 to 20 picojoule. It's much lower than the 125. How about the 32-bit addition? Just 7 picojoule. How about 8-bit addition? 0.2 picojoule. So that means the processor consumes very low energy to execute the simple operation, simple execution, or simple arithmetic operation. So why domain specific architecture? So actually we need so we can consume this small amount of energy for execution. But we need a large amount of energy for general execution of instruction. So that means if the large amount of data can be just executed in the processor, then it will consume very low energy. That is the idea of domain-specific architecture. So what is the domain-specific architecture? So domain-specific architecture is the architecture design focusing on the some specific domain application. So not one application. So if a processor can just run one application, that is ASIC, not domain-specific architecture. But domain-specific architecture just focus on the specific domain applications. So it is the many applications in the same domain. Okay. So that is why the domain-specific architectures are different from ASICs. So in order to design this domain-specific architecture, we need to know about the specific characteristics of domain-specific applications. Okay, that's why we need to understand the algorithm of the neural networks for designing neural networks accelerators, right? So example, neural network processor for machine learning, DNN accelerators, and then GPUs are very famous domain-specific architectures, and then programmable network switches and interfaces. Okay. So as you can see, domain-specific architecture is very hot recently in the computer architecture research, because we can make the more efficient processors with the domain-specific architecture. So we can apply, if we know some specific characteristics of these domain-specific applications, then we can apply the SIMD or MIMD. So we can apply the SIMD architecture for the parallel processing. And we can apply also MIMD architecture if the some applications require the fast single thread operation execution and by multiple users. So we can select the appropriate architectures based on the characteristics of a domain. Okay. So we can design some specific memory bus or memory hierarchy for the DSAs. So for the CPU, traditional CPU, we already learned about the memory system, that this memory hierarchy is designed for general execution of instructions. But for domain-specific architectures, for example, if we design the neural network accelerators, then we can design the purpose of this cache and internal buffer structures specified for some data movement of the matrix application or some systolic arrays. So based on some specific data movement or structure of the data, we can design the specific architecture of the memory systems. That is also benefit of the domain-specific architectures. And then we can eliminate the unnecessary accuracy. So we can reduce the bit resolution of the data. So for example, like this. So, and then as you can see, we can reduce the bit resolution of the data. We can save the energy very much. Okay, and then what is the important topic of the DSAs? We need the domain-specific programming languages like DSLs. So this DSL is different from C or Python, but when we design the domain-specific architectures, we need to consider programmability. This programmability is also very important. So we are designing processor, so not ASICs. So it's very important actually. So many vendors or many industry companies are looking for the compiler engineers for domain-specific languages, but it's very hard to hire recently. So with the domain-specific languages, we need to map this matrix operation or vectors or sparse matrix operation to some instructions and the data movement in the domain-specific architectures. So that's why the DSL is so important and critical. So these are the guidelines of the domain-specific architectures. The DSAs use the dedicated memories in order to minimize the data movement, because data movement cost is also very critical. And then in order to exploit the parallel processing or more efficient computation, domain-specific architectures can include more resources, like more arithmetic units or bigger memories inside of the processor chip. And then we can optimize the bit resolution to increase the performance and decrease the power consumption of the domain-specific architectures. Also, we need to develop the domain-specific programming languages. That's the guideline for DSAs. So, okay, so this slide shows the photos of the Google TPUs, the TensorFlow unit, tensor processing unit, and then Intel FPGA, and then NVIDIA GPUs. So these are actually the domain-specific architectures. So these processors run some specific domain applications. And then it is called the accelerator. So as you can see, so recently in the modern computer systems, the accelerator research is very critical and important. And then, so as you can see, these processor design and processor research is becoming the mainstream of the research trend in the computer architecture field. Okay, so this is the end of the today's class. So in the today's class, I introduced about the domain-specific architecture and then why domain-specific architecture is required in the modern computer systems. Okay, I hope this video has been recorded well. So then in the next week, let's meet with the Zoom meeting, so real-time Zoom meeting. And then, okay, see you in the next week.